So I guess let's start with just introducing ourselves. I'm Chris Redino. I'm a particle physics PhD, theoretical physics. I'm interested in a lot of industries, so as long as you give me a challenging problem and I can do some modeling, I'll be happy. So that's me. This is Amy.
I'm Amy, and I just got my master's degree in statistics, and I'm really interested in data visualization, and I have experience in marketing and sales. I'm really interested to do some machine learning projects on this area. And this is Brett.
Hi, I'm Brett. My background is in law and entrepreneurship and computer science. I'm a former lawyer. I've done a couple startups in the legal technology space, and I also have a computer science master's. In terms of interests, I suppose I'm probably most interested in leading data science teams, given my grayer hair than some of the other folks in the room. But I'm looking to explore all sorts of exciting opportunities in this field.
And for our project together, we were trying to improve the Home Depot search relevance. Okay, and this is another Kaggle competition, so the goal is to predict the relevance of search results on HomeDepot.com. Maybe it looks a little better here. So just, on their online search, and the idea is if we can improve this, then people will find what they're looking for faster. Okay? And in terms of what we're given, this is what our data looks like mostly. So we're given a product title, a product description, what the person searched for, and for our training set, we're given the answers. We're given a relevancy, okay? And this is a human scored relevancy. So you'll notice the product titles repeat, okay? The searches repeat. Each row is a unique combination. So each row is like a single hit on your search engine, a single hit on your search results, okay? And we're trying to predict this for new searches. That's the idea. And you'll notice this is on a weird scale. It's 1 to 3, okay? So 1 being not relevant, okay? 2 being somewhat relevant, 3 being very relevant. But it's not discrete, it's actually continuous. The reason you have multiple bars here is because for the training set, what happened was humans just looked at what the person searched for and what the item was, okay? So like they just read this and say, is it relevant or not, okay? And the reason you have stuff in between 1, 2, and 3 is because they actually took the averages from a few users. And some of them had, most of them had 3 users, some of them had more, that's why it's points in between. So we're trying to predict something continuous, but our training set's actually somewhat discrete, so this is kind of hard. So we might predict something like a continuous distribution, but we're actually trying to fit to something that's spiky. So this is difficult. And it's not just difficult for us, this is difficult for everyone. So if you look on Kaggle, yeah, we're just outside of 10%. So there's, many thousands of teams competing. But you'll notice our scores are not much different. It's a very flat distribution of scores. Okay, this is root mean square error on that prediction. So this is tough, okay? So our workflow, our approach to this, the basic workflow is standard for model building. We start with prepping the data, then we build some features, then we use some algorithms with these features, and we ensemble our results from these algorithms to get some result. Okay, what's a little different is how we divided up the work between us. I think what a lot of people on Kaggle do is they'll divide the work between members among the different algorithms. Okay, they'll each have their own model. Instead of doing it in parallel like that, we chopped it this way. Okay, so I did the data cleaning. Okay, Brett had the human-made features. Amy also made features, but she did it in a more automated way using some packages. And then Amy put the models together and we ensembled. And the reason we do it this way, the reason we decided to do this was it gives us each a different perspective on the data. Because when you're cleaning, you're going to consider different features of the data. When you're building features manually, you're going to consider different things. And when you choose your model, you're going to consider different things. So the idea is we all get different perspectives and we all talk to each other. So this isn't something, these aren't steps that just happen one at a time. Okay, these are steps that we constantly have feedback. So as Brett keeps making new features, I keep coming up with new ways to clean it, and we keep feeding it forward and talking back, okay? So that's probably the most novel part of how we do this. So I'll talk about my text clean briefly. So the idea is human language is very ambiguous, okay? If we want to have searches actually match each other, we want to reduce that ambiguity. So a cleaning step could help a result, it could also hurt a result. So we want to try different things and try different combinations of things. So these are just some basic ways to clean the data. So you could fix all the casing so you don't have to worry about that. So like hammer to hammer, okay? You could remove symbols that might make things more ambiguous. So all instances of feet are not going to have the period, okay? You can remove stop words. Stop words are like noise, basically. So words like for, it, to, things that appear so frequently, they're not going to be useful, okay? We can do part of speech tagging, okay? So a hammer is a noun. This is especially hard for the Home Depot set because a lot of nouns are verbs, hammering things, drilling things, etc. So this is, again, this could help, but it could also hurt. So all these steps are kind of double-edged swords, okay? Lemmatization and stemming, these last two, these are both ways of changing a word into its root word, okay? And this is kind of why we need this part of speech tagging. This will help us do this. So lemmatization just kind of looks up what the root is. Stemming is a different way to do this, and does it by cutting off the end of the word, okay? These are easy ones. We might want ones that are more specific just to the Home Depot set, so we'll have to, these are pretty automated, but I could also make my own lookup tables, my own dictionaries to actually do the replacement. So the first one, replacing numbers, that's also pretty standard. This is pretty easy. The rest are a little more difficult. So what's especially used for the Home Depot set is standardizing measurements, okay? The phrase 2x4, okay, like a piece of wood, there's actually over 1,000 ways I could represent this string in language, okay? And I'm trying to reduce all those to just one consistent format. So if someone searches 2x4 in any way, I know what they're talking about. That's the idea, okay? And you notice one of the ways I make this uniform is I just throw off the units, and that's because some people won't use units, okay? That also means I introduce a little more ambiguity, so it's double-edged, okay? I can split join words, and which words are joined, that also depends on the data set. I could correct spelling, there's different ways I could go about this, and I could reduce the synonyms, and we have very field-specific synonyms, so like loppers are the same as shears, approximately, okay? So that's what I did. So what I do is I take those first three columns, I transform them, and then I hand them off to Brett, okay? So handing off to Brett.
Got it. I dropped it. I said got it. I went like this. So yes, that's right. Chris talked about sort of the handoffs that we were doing, and I was responsible for the feature engineering piece. It's a little bizarre to have this on both sides. I don't think I've ever done this. It's like we're like surrounded by our projects, enveloped. The one thing worth mentioning before we sort of dig into some of the feature stuff is that when we say feature engineering here, something relatively unique, not completely unique, but somewhat unique, is that our feature engineering was really feature creation. We got no features from the project. They gave us search terms, and they gave us product titles and product descriptions, but none of those are features. We had to create all of the features ourselves. So this wasn't a question of sort of manipulating features and doing combinations and transformations. This was, okay, what are we going to use as features from the get-go? So it was really feature creation. And also worth keeping in mind is sort of as we got started with feature engineering, some of the things that we had to think about as objectives with respect to feature engineering, and that's a little bit of what you see here. We referred frequently to the upper left problem that we kept seeing, which is the upper left of this plot that you see here. We kept doing sort of simple things in the beginning to see how our features were doing, and we do things like simple stuff like, okay, how many of the search terms are matching how many of the product title terms? And we kept repeatedly seeing situations like this, where the performance wasn't bad at the higher levels, when we're matching 8 or 10 or 12 terms. Yes, we'd see some pretty good results that were pretty much up here in the 3 range, and not so much down here on the bottom, where we're getting lower scores. But at the lower end, the converse wasn't true. That is, when we had very low match counts in this example, we'd still see the distribution across this whole range from 1 to 3, meaning lower match counts didn't equal lower scores. We still had a distribution here. So it would make sense for these to be down here, but what's going on up here? Why did we continuously have this upper left problem with low scoring on what we were trying to use as our predictor, and with respect to high scores on the response? We couldn't fix this upper left problem. Or I should say, we kept trying to fix the upper left problem. The other point worth mentioning, and Chris showed you this plot earlier, this density plot, shows you in the background the distribution of the training set. You can see it was very spiky. That overlaid red piece is the distribution of what we saw on the test set when we ran our results. So you can see we're clearly, we literally, 3 is the biggest response in the training set, and we're getting very few 3s, just a couple of them on the test set. So something's wrong there as well. It could be that Home Depot was smart enough to pull out a distribution of the test set that's dramatically different from what we saw in the training set. We played with some of those theories for a while. It's not entirely clear still. As Chris also mentioned, this is an ongoing competition. We're still working on it as recently as this afternoon, and he's plugging things into our machine learning models. But these are some of the things that we're struggling with as we're thinking about what the best features are. The features in the end are, for the most part, not terribly complex or not terribly surprising, I don't think. It's hard to differentiate on this stuff with respect to other teams, although we did some things that were somewhat unique. I won't go through all of these, but a couple of them are worth mentioning. Some of them are obvious. Matching words directly, I think, is pretty obvious. We were able to get the brands, so obviously if there's a match on the brand, we want to use that. One of the more unique ones, and I'll admit this was not something that we came up with, but we saw it referred to in a couple different places,
was this idea of a last word match. So that if the last word of a search term matched a product title, for example, the thinking is that that's somehow more powerful because that's likely to be the direct object. I want a red board. Well, if red's a little iffy, but a board, okay, that's a better match. The last word in the search term was thought to be more powerful. And we saw some of that, but it didn't really make too much of a difference. Some of the ratios, I think, are also fairly self-evident. How many of the search terms are we matching in the whole search string, the whole phrase, how many words are matching? How many of the target words are matching? So the product description, the product title, what's the ratio of words being matched? Again, not terribly surprising. The length of them, again, is also not surprising. I will mention a couple more here. Synonym scores is kind of interesting. Chris was modest when he talked about some of the work that he did in trying to find, I think, what was your example? Your last example of your synonym finding.
Loppers and shears.
Thank you, loppers.
Yeah, I didn't know what loppers were before.
You said that like it was so obvious. Well, loppers and shears, same thing. I still don't know what a lopper is, but
I think loppers are for thicker branches, and I'm not sure. Yeah.
Any forestry expert? Oh, we've established that anyway. But Chris went through, what I did is I pulled out that upper left portion that I saw, or at least I tried to, and I gave Chris a set of 1,000 observations. And Chris said, okay, these are the ones we're having trouble with. And he went through and manually said, okay, what are synonyms that we can use as grouping mechanisms for these words that mean different things? Trying again to say, well, okay, if you're going to put lopper in, well, that's a good match with shear. We should recognize that.
Jump in. 1,000 seems like this is a stupid amount of manual labor, but it's actually really smart because we've targeted those 1,000 which are useful instead of looking at the entire 70,000. So.
Yeah, that's what I said. I gave Chris the upper left piece. That's the piece that was the thing that we were having problems on. Why are we getting low match counts and high relevancy scores? We must be missing something. The search must have been lopper when it was really shear. That's why it's low on our count scores, but it got a high relevancy ranking. So it made sense to go through that 1,000 separately. And finally, we'll talk about word power scores. This is something that we came up with that we thought was kind of novel and we hoped would change the world. It did okay. I don't think it necessarily changed the world, but it's somewhat interesting. And this refers to this idea we had that certain words are just better than others. If you're searching for a certain term, it could be that that term is very powerful and very likely to generate high relevancy scores. So if we see that word in the search term in the test set, we should give it a high mark. And we did that. There's a couple ways we could have done this. I started by doing it sort of manual dumb, like silly loops and things like that. The computational cost was huge. So I actually wound up using the TM package in R, and as you know that, it's typically used for term frequency, inverse document frequency stuff, TF-IDF. I see some heads nodding, so you know about that. I did not use it for TF-IDF. If you think about it, that has sort of weird application here. But I did use it for a simple grid. It's a document term matrix that I used. So you see here, I'll use this one because it's not cut off. It's a whole bunch of zeros, but each one of these is an observation. This is each word that was searched at any time, and the 0 or 1 just means whether it was matched. So we're able to go down, here we see a 1. Why somebody is searching the word Zen on Home Depot, I have no idea. Looking for a Zen hammer experience? I don't know. But apparently somebody did. So we were able to go through and say, okay, what's the average on the far end of this? You see the relevancy score, that's here. What's the average relevancy score anytime anybody searched Zen? So in this case, there's a 3 for Zen. I looked them all up and got an average score, and then I added them all up for each search term. So if the search term had Zen and hammer, I'd add the Zen score and the hammer score to come up with a word power score for that search. We thought that was kind of novel and kind of neat. And it performed fairly well. My job, after we've in the end had about 20-some features, the idea then is pass it to Amy, and Amy would run with it from a machine learning, don't drop it.
Yeah, okay. Okay, that's, I want to drop it. Okay, I can put it here. So for me, actually, I'm using model building and selection. Actually, what I've done, I first using text mining to build our features. Because Brad already does the numeric features. It's per like a human being's perspective. Actually, we want to do like, what if we just threw it in a model or like a TF-IDF or doc2vec? Maybe it makes some sense that we didn't capture that part of features. And then I put it into different models. And finally, actually, I select random forest. I will tell you why. So first is TF-IDF. It's a very traditional topic in text mining. Actually, you're using TF to show the word, to calculate the frequency that word in different docs. And you using IDF this part to punish the word that appears in all the documents, like is, that didn't say anything. So actually using TF-IDF, we get the most important topic, like this word shows a lot of times, but it's not stop words. It's not is, that. So it's have some important features. But I think TF-IDF is that it didn't calculate the distance between the docs. I don't know if I say clean, maybe it's somebody said it's pretty nice. Maybe clean or nice have some distance. It's positive, and the clean with something like dirty is totally negative. So maybe there have some relationship between the different important topics. So I'm using doc2vec. Here is a very nice graph that shows you, and you put the document into the doc2vec. Actually, why is doc2vec? It's not doc2vec. It's two vectors. So actually, we built a vector for different docs, and you can see there have some topics. We assume there is 200 topics in our search term, in our all the text features. Then you can see there have relevancy. When you pull the France, actually you found Paris. It shows with France here actually, and you can calculate the similarity between these words. It's cosine distances. So I'm using doc2vec build two things. This first one, I think it's cut off. First one is distance. So I using product title and product distribution description to find if it's relevant to the search term. And second one, I using cluster data. Actually, we're still doing that. We wanted to using the cosine distance to find which search term, which combination is more get a relevancy. So I'm still doing that, and you can see this is a part of our graph. This is different groups. They are sort of together because actually I'm using 124 dimensions to show that, but human couldn't see that, so I just using a 2D dimension to show basically the groups. So after that, I do different models. That's all the model combination that I tried. I'm using different types of clean data from Chris, and I'm using different numeric feature from Brett and combine with my models. I tried XGBoost first because I wanted to get the result as soon as possible, because XGBoost is deep learning stuff. But the method didn't come out quite good. I think about that. I think that's because this training data set is smaller than test data set. So if you do deep learning, you just capture all the features in the training data set and you're overfitting the training data set, so you couldn't capture the relevant feature in test data set, so you're overfitting. So the score actually is pretty bad for XGBoost. I think it's here. It's 0.54. It's just doesn't make sense. So I was thinking using gradient boost or random forest. Then I find the gradient boost is much work to do because we have a lot of data. We have ensemble text mining like doc2vec and TF-IDF. That's too much work and too many things to tuning. So I think because we have only 1 week to do that. So what I did is I using random forest to make it simple. So you can see the best model here actually is a green one here. I using random forest with TF-IDF. Ensemble with my the distance I got from doc2vec. And also I tuning the weight of the description. So actually description can tell you something about the model. I'm still doing that. It's something I haven't finished yet. So to tell the just briefly tell about the best model we have is we do an LP process to get numeric features, and doc2vec to get distance, and TF-IDF to tuning the weighted of test. Then I assemble them into random forest to get the result. So this is a part of my code, just little part of it. I have to say I'm really surprised about this part. I give description. Okay, this is not just I tuning. It's just not 100%. I just tuning by my just change the number like a gradient boosting by myself, because the whole model takes me almost 1 hour to run the whole process. So I give the description like a 0.5 or 25. It's just to make it better. So I think in the future I will put the model in some with others. Like I will put it with. I was thinking use a factor analysis to make sure which features that's used most for this data set, and makes the model more interpretable to tell others. So that's all. And yeah. That's
Questions, anybody? Yeah.
Yes?
You know the table batches one with the original, no, sorry, the table.
Oh, the tables? Okay.
Yes. Okay, so for the input, I see raw data and clean data, and then for feature, I see others and ours.
Yeah.
So there were models where you just use the raw data.
No. Yeah. Because for text mining, sometimes raw data will give you more features. Someone's typo or something just to give you more features. If you clean it too much, you just lose the features.
So the raw data was put into that.
Yeah, actually the numeric features like others is what we already got. Ours is just what we have a new idea, just separate. So
sorry, what's others?
Others just the features that we already got, like how many the search term, the ratio, other things that's a very natural that the people will come out, and others like word power or other like last word match. That's features that people will think about it and it comes out. So sometimes I just others means I have to just put that features into it, and ours means the new features.
So what's the difference between input and features? Because from I just heard features are.
Input is just for my text mining. So like a doc2vec, TF-IDF. So
Input's the original 3 columns. Features are what are the contents of the additional columns. So we could make our own, or we could either look at what other people have done on Kaggle, or we could generate the other features from using something like doc2vec. So there's different ways you could generate the other rows.
yeah, we're using different version of our data to
And
make it a combination. We don't use the cleanest or the best. Because we don't want to lose.
That was the subject of considerable internal debate. How much cleaning to do, and you heard Chris say a number of times, well, there's a double-edged sword here. If we cleaned it too much, we might be breaking connections that existed. So we were constantly struggling with how much elbow grease to apply to the cleaning work and the work that I was doing on the feature side versus just send it through.
And it's not just clean or raw, it's
Right.
degrees of clean. And different steps, they make some search results worse, while they make others better. So actually ensampling over your different levels of clean, that might help.
And the order in which you do it, if you lematize and then stem versus stem and then lematize, etc. All that makes a difference. Poor Luke is laughing.
So what made the most difference? Because the distribution of scores, it seems like all
that's-
more or less at the same effect.
Yeah,
Well,
that's
Yeah, they all look pretty close, but if you...
that's why we like the
This is the same
foundation.
thing Thomas was saying. If you're really getting into the Kaggle, you're fighting over, look at
Look at
how different are we from the person above and below us, okay? It's only in the 5th decimal.
And
So-
the number one score is 0.44.
Yeah,
We're at
they're-
0.47.
We're within a
We're
percent.
200.
You guys did fantastic.
Yeah.
No.
So when you say it all
No, no,
looks
no.
when you say it all looks the same on that last slide, those are actually huge differences for this competition. That's the point.
Yeah, we weren't being self-promotional there. We're making the point that these are bunched up so tightly in the real
Yeah.
world outside of just our own scores. So
These
that's why
are
it's
these are big differences now, not small differences.
And that's an enormous difference, that 0.54.
So what do you think matters the most?
So far, I think Amy's model tuning is doing the most, but we think we're at the point where the point is the cleaning and his features are very dependent on the cleaning, and the cleaning is very dependent on where you apply it. So we're still getting to the point where I think that Amy's model could best utilize me and Brett's part. So yeah, it's like we're trying to catch up.
You heard Thomas just in the previous presentation said feature engineering did not seem as significant and have as significant an impact as machine learning model tweaking. But we're seeing similar things. Although we do think that, as Chris said, combining the right feature engineering with the right model tuning obviously is also.
There's lots of permutations here, and we've only tried a handful of them. That's the idea. So if we have more time just to fill in these permutations, I think I think we could do better than 10%.
Do you guys also use H2O?
No, we did not.
What do you use?
You ran it on a cluster, right?
Yeah.
Yeah.
What?
So a forest is really easy to parallelize, right? You just give different trees to different nodes.
Sure.
How do you stand against other competitors?
Oh, so yeah, that. Yeah, so we're at this one's easier to read. We're at about 200, and I think there's over 16 now. So this is at this point in time we are at like 12%. But where we stand, everyone around us, it's pretty flat, and the best person is 0.44. So that's the root mean square on this 1 to 3 scale. So 0.44, that's still really big. Even first place is doing really badly, if you want to think of it that way.
On a scale of 1 to 3, the best performing team is still half a point away.
Yeah.
So
Half a square point. So
Yes.
yeah. So yeah.
we refer frequently to how close we are to number 1. It's just this close to number 1. We're equally close to number 1700, but we don't really like to think
Yeah,
about
yeah.
it.
So
Sorry.
yes.
I know that Kaggle doesn't allow you to use external data sources, but if you could, what would it be?
Oh, this is really easy. So I think one reason this is really hard, it's not just because people have really terrible searches. That's one reason. The other reason it's really hard is those human reviewers, they actually had photographs of the products. So even like some of these we're looking at, like, how do you know this was a 3? I have no idea what this thing is he's searching for. But then if you see the picture, like, oh, I could kind of see what he's searching for. So I think if you actually did this as an image processing project, it would be easy. I mean, it's a harder problem, but at least you're approaching it in the right way.
Yeah, I'm sorry, go ahead.
If we have pictures, we can do randomized LBA and to generate features and through the features into our model. That would be more easier to do that. But the thing is, we're limited to the words.
Yeah, that's illegal.
Just to sort of get a sense of how the search terms matched up with the product titles and descriptions, I went ahead and went online and put in the product titles to see how they were matching up. And I encourage you to do that if you're interested in this sort of thing, because I found myself completely ignoring the words and only looking at the pictures. And our challenge was to match the words, but even I, as a competitor, couldn't help but look at the pictures and say, oh yeah, that's a good search, that one makes sense. I can see why they gave that a high relevancy score. And I was basing it on the pictures when I know that I shouldn't have been. The temptation, the picture really is worth it, doesn't work. So Chris is absolutely right about
And
that.
it comes back to one of the problems with the text is language can be very ambiguous. A picture is not usually as ambiguous.
So Google open sourced their picture search algorithm. Did you ever think about to bend that algorithm?
Well, we that one came up. We're not allowed to bring on outside data source. We're not allowed to use the actual photo data
It's fine for own fun.
for fun. This is something we could pursue.
Well, but
right now we want
wouldn't have their pictures. In other words, what we need is the picture that the human reviewer saw.
we would
The
have to
human
make
reviewer saw this search and this picture and this title.
we could make
we
a
had
script
we had
that
the search and the title.
feeds all of them into the
we need the
website.
picture that the reviewer saw in order to do that as
Yeah.
effectively as we really want to.
Yeah, we don't have the list of pictures. We have the list of searches. We could put them all in here and get that list of pictures.
We can script